Here's the start of lecture. Oh, that means people watching won't get to see broccoli. Oh, if ever there was a reward for coming to lectures live, you all get the songs and the animals. Subject evaluations, you can still fill them out. We are still very excited to read them. This is the last time I will tell you that in a lecture. So what are we gonna do today? We're not gonna do anything new today, really. We're just gonna wrap up some stuff about O33. I'm gonna kind of remind you of all of the stuff that you've learned. I will pay maybe a little bit extra attention to the second half of the semester since, I know you have an exam coming up. But I want to talk about some stuff that we haven't really been able to synthesize as part of O33. And at the end, we're also going to talk about, if you liked this class or just parts of this class, some other classes that you might take at the end. And there's a couple of us here that I'll tell you about specific classes. So this might not take the full 50 minutes, but that feels fine. All right, so let me remind you of what you know how to do. All right, so first lecture, day one, we talked about modularity and abstraction, right? And we talked about using that to decrease complexity. So let's see how we did it. How did that come about in this entire class? When we started out with the operating systems, it's been a while since you all have seen this slide, right? But operating systems are all about abstraction and modularity, right? The literal job of an operating systems kernel is to enforce modularity between user programs, between itself and user programs. That's what virtual memory, bounded buffers, threads, all of those things are doing for us. Without those things, user programs could easily get in each other's way, right? Or corrupt each other in some ways. Right, when we move to networking, modularity and abstraction maybe start to get a little bit less obvious here, right? In part because I wasn't saying the words enforce modularity in every single lecture. And because we had to start dealing with some additional concerns, right? This is where the world starts to get in the way. So economics, scale, all of this stuff. But what you saw over and over again in the networking part of the class is a lot of layering and a lot of hierarchy, right? Which are examples of abstractions. You've seen this, like in the networking stack, DNS, even in routing and BGP. You've seen some other nice abstractions here too. A reliable sender and a receiver, that's a good abstraction to think about. Once we got that to work, our applications could, more or less rely on the network. We had that layered model. You could build things on top of the abstraction of a reliable transport system. Right, so then we can default tolerance, distributed systems, this section that we worked on for a while. And sometimes I will have students tell me that this section feels kind of messy to them or complicated in different ways. And I totally get that. There's so many details that we have to get right. But remember that the whole goal of this section was to enable what was ultimately an enormously simplifying assumption, right? That we would have transactions that would give us atomicity and isolation. If we don't have atomicity, the reasoning that we would have to do surrounding failures would almost be impossible, right? There would be so many different situations that we had to try to deal with, right? We would have had to take into account every possible stage of a failure within, a sequence of steps. But when we have a transaction, we don't have to do that. Either the whole thing happened or none of it happened. Without isolation, it's so hard to reason about concurrency, right? We saw that back in the first part of the class. We saw that with locks. In operating systems, locks were kind of a concern for us. There were senses in which they kind of broke modularity. They involved a lot of global reasoning and they were kind of messy. But when we get to fault tolerance, we get things like two-phase locking. It still uses locks, but it gives us a systematic way to apply them. Right? Now, you've also seen examples of abstraction and modularity in papers in recitation, right? Systems like MapReduce and GFS, they abstract failures away from the user. In fact, GFS abstracts certain types of failures away from MapReduce, right? A MapReduce job can run on top of GFS without having to worry about, say, losing the input data or losing those final results. The data is stored on GFS. That takes care of replicating it, dealing with machine failures. And then the user running the MapReduce job doesn't have to worry about machines failing during that job. MapReduce abstracts all of that away. It's going to rerun the jobs. It'll recompute any results that are lost. It just handles it. And then when we get to security, things do get a little bit trickier, right? modularity and abstraction get a little bit harder to recognize here. But to try to design good, secure systems, we want to start out with these modular designs. We want to understand how the components, the modules of our system interact so that we can understand, where they might be open to certain types of attacks. Right? So modularity and abstraction, they have been with you every day of this class, even if we haven't used the words. But then, what about all of these other design principles that you saw in the first lecture? Right? We've talked about these a lot, but where did they really come in? Right? So we'll start up here with scalability. Right? You saw this in so many places, but really most often the networking section, right? Because that's where we started to move from just one machine to a lot of machines. Right? So maybe the first place where we started to think about scalability was with DNS. Right? DNS was designed in response to the needs of a growing internet. Hierarchy, including this kind of hierarchy of management, right? The fact that zones administer themselves, that enabled DNS to grow even bigger, right? So we definitely saw issues of scale with DNS. We also saw them when we got to routing, right? We talked on the first day of routing about link state and distance vector. Neither of those are going to work across the entire internet, right? So we talked about having a hierarchy of routing, right? Typically doing something like link state within an autonomous system, so like within MIT, and then having other protocols, BGP across ASs. We talked about path vector routing, which is BGP. BGP is a path vector routing protocol. We talked about how addressing works, right? So we had to make all of these decisions to get these protocols to work at scale, right? Even TCP is another good example. We don't always think about TCP as, an issue of scale because we're typically thinking of sort of an individual sender and an individual receiver. But the fact that we're thinking about them as individuals is what enables the system to work on the internet. A reliable transport protocol that required some sort of centralized coordination across the internet, it wouldn't happen. It's too big, right? We were forced into this place where endpoints had to make their own decisions for the most part, right? Individual senders are making decisions in TCP. Coordination would be too much, right? And then even when we went to delivering content on the internet, right? Remember the first day when we were all buying llamas, we had like one client and one server. And that's not enough. That's not going to grow Katrina's amazing web suite. So we looked at all these different examples, right? We went through CDNs, content distribution networks. We went all the way to peer-to-peer networks to think about just different ways to deliver content to a lot of people at once, right? Even outside of networking, we dealt with scale. One of the reasons, not that yet, one of the reasons that we started caring about fault tolerance and building large distributed systems was so that we could scale to more users. Right? And then even in security, we had issues of scale sometimes. Right? Remember when we were thinking about signatures? We wanted to use signatures so that users could verify who they were. But we need some way to distribute those public keys. So we had to think about, well, if we have a certificate authority, which is not perfect, but let's say we have that, how does it manage being the place that distributes all of these messages? All right. But it doesn't have to be. Right? By signing messages, can give them to users to distribute on their own, right? Because of the nature of how the signatures work. The certificate authority itself doesn't have to be the entity distributing these messages, right? So you saw scale. I mean, I'm picking out some examples, many of the examples, but not all of the examples, right? We saw scale in a lot of places, right? So then, all right, so that's scale. Scale came up a lot. What about fault tolerance and reliability, right? Notice that we didn't really start talking about fault tolerance and reliability until we also started talking about scale, right? As we start to see more machines, more users, more data, that's when we start to see more failures. And we really got started with this in networking, right? We talked about routing and reliable transport. Routing protocols can adapt to failures in the network. Reliable transport decreases the probability of long-term packet loss, right? But of course, we get much more into this in this distributed systems part of the course. Right? So in the lecture, our goal was to implement these transactions, provide atomicity and isolation, right? That makes it easier for us to reason about failures. I'm going to go through this slide a little bit, just in interest of sort of helping remind you everything you learned in preparation for the final. We first saw atomicity with shadow copies, right? This is kind of a copy on write mechanism. And it worked okay for a single file. It rested on the fact that we could rename that file atomically. That rested on the fact that a single sector write is atomic, right? So we got these big systems because we could rely on this very, very small amount of atomicity from hardware. But those shadows copies didn't work well for big files. We have to do a change for every small write. We have to copy the whole file, right? So that's when we moved to logging, right? And with logging, we added caches, we added cell storage to improve performance. So we're appending updates to a log, and then we have these additional structures that help make reads and writes and even recovery a little bit faster. And once we started to distribute those systems, atomicity and isolation started to get more complicated. Because once we're distributing a system across multiple machines, now we have to make sure the logs agree across those machines. And there's a network between those machines, right? And networks aren't perfect, right? So that is where systems like two-phase commit come in, right? We use two-phase commit to get multi-site atomicity. So to guarantee atomicity across multiple machines, even when there's a network in between those machines. Two-phase locking, right, is different. These are not the same protocol. Two-phase locking gives us the isolation piece, right, by creating these conflict serializable schedules. I remember that was just one choice of how to handle isolation, but that's how we got it to work in lecture. And in this world of two-phase commit and two-phase locking, even though we had all of these machines going around, we were still thinking about a single piece of data existing only on one machine, right? So we had our data spread across a lot of different machines, but the variable X only lived in one place, right? But we know that that's bad. We want replication, right? You saw that in a single disk with RAID, a single machine. So we brought replicated state machines in, right? That's what those are for, to solve that problem, to let us store data, to mirror data across multiple machines, but still have a way to think about well, when is data readable, right? When can users see these writes? All right, so this lecture has a nice story, right? It flows through this slide. So what happened in recitation, right? How do the recitation papers fit into this diagram, right? Well, one of them is just sort of the final part of this slide. Okay, Raft has this direct tie into lecture. It solves the problem of a failing view server in a replicated state machine, right? That is the one thing in lecture that I did not give you, right? We had to assume that view server was going to be up the whole time. Once you have Raft, you don't have to assume that anymore. But what about all those other papers, right? MapReduce, GFS, ZFS, they all give you examples of real world reliable systems that are making different trade-offs than what you saw in lecture, right? MapReduce, it's meant to implement a particular parallel programming model, deals with failures within the constraints and the assumptions of that model. GFS is, I don't really want to say that GFS is more general, but it's, instead of attacking a specific problem, it's meant to be a file system, which you think about, that's a little bit more general maybe, but it also relies on some simplifying assumptions, right? Assumptions about what writes to that data is going to look like, assumptions about reads of the data, right? ZFS, you see us push transactions into file systems and some of the stuff that comes along with that. Even the baseball paper, right? The consistency models, through baseball, shows you examples of other styles of consistency that we consider in the real world, right? Single copy consistency, which that paper calls strong consistency, is one of them, but it's one of a bunch, right? So ultimately what you saw in these recitation papers for all of these distributed fault tolerant systems are options for relaxing. We don't always need single copy consistency, right? The baseball paper shows us that. We don't always need conflict serializability. We don't always need to support transactions in a system that has the absolutely most general read-write patterns, right? GFS gives us an example of that. What you should take away from those papers is the gains that you get from relaxing some of those constraints and assumptions. Your system is going to be less general, right? GFS is a great example there. GFS isn't meant to be this all-purpose, completely general file system, but it gets a lot of gains for when it works in performance and in simplicity, right? So those systems are all about illustrating these kind of real-world trade-offs, right? Now, this is fault tolerance. What about security? Right? So in lecture, we looked at a bunch of different policies that we could provide and a bunch of different threat models, right? We thought about an adversary, say, with access to stored data on a server, right? And they could get that access maybe because they're meant to have it. They're someone like a system administrator, or they're doing some style of attack like a stack smashing attack, right? To secure that data securely, we want to be storing something like salted hashes, right? It doesn't make it completely 100% impossible for the adversary to ever figure out, say, our passwords, but it makes it very difficult for them and very time consuming. It makes it much harder to, say, pre-compute hashes when they're salted, right? And then we thought about adversaries in a network. At first, these adversaries, they were mostly observing data, they were tampering with packets, right? Secure channels protect us against those things, but we kind of have to take care there to understand exactly what each cryptographic primitive provides us with, right? For example, encryption only gives us confidentiality. It does not also give us integrity. And we saw that, along with that, we had to worry about how we do key exchanges, right? That's an important part of the process. If we're going to rely on a shared key, how do we share the key? Right? We talked about having to verify identities of the people that we're communicating with. Otherwise, we're open to, different types of adversaries. Then eventually our adversaries moved to trying to infer things about, kind of about packet headers, about who is communicating with whom, right? And we saw Tor there to help deal with that problem. Tor doesn't provide us with full anonymity because of those timing attacks, but it does help, right? It gets rid of a lot of kind of the easiest attacks. Right? And then we moved on Monday to kind of like the biggest network adversaries, right? Network adversaries who had a different goal. And their goal is to bring down some sort of legitimate resource. So secure channels and Tor, they don't help us here. Right? The adversary's goal is not to examine packets. It's to congest the network or exhaust state or computation or something like that. Right? And we can build systems to try to protect against those things, to try to detect them, deal with them. Those systems can be complicated, right? And this also kind of gave us another motivation to go back and think about these distributed fault tolerant systems, right? A well-distributed system is more resistant to a DDoS attack than a single centralized service, right? And I think there are times at which the security section of this class can almost be depressing, right? Because it feels like, every time I show you all a solution, there's a new attack, right? You might think that it feels depressing. And you saw more details of that in recitation, right? Meltdown gives us a different style of low-level attack than what I showed in lecture. Mirai gives you a specific style of botnet, right? DNSSEC, is a solution to securing DNS. It is not fully deployed yet, right? But remember that we can make improvements, right? Many of the attacks that you hear about in the news are really not that sophisticated, right? We can store salted hashes, right? That's going to make it much, much harder for adversaries to steal our data than a system that is, just doing regular hashes, no salting, right? Now, for performance, you've seen this everywhere. We cared about performance with logging. That's why we added the cache. That's why we added self-storage. We cared about it when we were replicating data. We cared about it in MapReduce. We were constantly concerned with things like latency, throughput, utilization, even when we didn't call them out explicitly, right? In fact, one of the reasons to think about these distributed systems was to improve performance, right, as the number of users is growing, right? So those are the four kind of, design principles up here. But what about this last one, right? How do our design and implementation choices affect people and communities? And who makes these choices? So in my opinion, this is the most important thing for you to think about as systems designers. We have been subtly calling these issues out in almost every lecture and recitation. That was my goal for this year. Since we've been doing it subtly, now I'm going to do it explicitly. Right? So who is affected by our decisions? Right? Certainly the people who use our systems or rely on our systems in some way. Right? So remember one of the early in the news segments when some of the vaccine websites crashed. Right? They crashed because they couldn't handle the demand. They couldn't scale. Right? The ones that could scale were backed by companies like Amazon and Google. Right? And that has its own challenges to deal with, but the lack of scale in these sites had like material consequences for many people. All right, you all know about my current favorite news item, right? This gas pipeline, right? The attacks on the gas pipeline has led to people in the southeast of the US, kind of panic buying gas. Planes have been rerouted, all of this kind of stuff. Right? You saw an example just on Monday when I showed you the article about, a botnet that was set out to attack the energy grid in the US. And we also saw this internet outages in Maine, right? Right now, an internet outage, it's not a mere inconvenience, right? It means that people can't go to school, they can't go to work, right? But, the world beyond just the users of our system is also affected by the decisions that we make, right? For instance, in your design projects, we asked you to design a system that only ran on phones. And that's fine. That is exactly what we asked you to do for this project, right? That is how we scoped out this project for you. But at the end, we also asked you to consider what would happen to users without phones, right? Were there any benefits that they could still gain from your system? Were they still a part of your system? Maybe your system freed up resources that could be put towards people without phones. For instance, in the exposure tracing example, perhaps a system to do exposure tracing on phones can be done in conjunction with more traditional exposure tracing, where we have people going door to door or making like actual phone calls, not like app-based things, right? Or do the decisions to use these systems disenfranchise certain people or communities? Do they leave them out of the benefits, right? Beyond even just people, right? Remember these headlines. It is funny to think about beavers and sharks attacking the internet. Like, it is objectively funny. But these systems that we build, they also affect the environment, right? We put physical infrastructure out into the world. So once you start thinking about these things, it's not that much of a leap to see that the decisions that we make when we build these types of computer systems affect humans, they affect society, they affect the environment, right? Especially because these systems back most of our everyday lives now. And a lot of times the effect on people is actually kind of aligned with our general design goals, right? We want to design fault tolerant systems because we don't want people to be impacted by failure. We design secure systems because we don't want our users' data to be stolen, right? As system designers, we hold a lot of power. We affect a lot of people's day-to-day lives, right? But the impact of our design decisions, it goes beyond just enabling or disabling users from having a certain experience. There are times when our technical decisions lead directly to certain types of power structures, right? So for instance, when we talked about DNS again, the hierarchy of DNS is there in part to allow it to scale, right? And it works. This is great. The hierarchy also creates a root zone. And then you have the question of, well, who should own the root zone, right? And what type of power does that give them? Right? When we talked about content distribution, and we looked at all of the different ways to scale that distribution, peer-to-peer networks have this like fun, organic kind of feel, right? They don't involve like a company the way that a CDN basically always does, but they make it hard to offer performance guarantees, right? Because end users don't have very good upload bandwidth, right? And that's for many reasons, including the way internet is sold, right? Even more subtly, we talked about layered models for networking. Layered models are very cool. They let us swap out functionality at the different layers. They let us rely on things at a lower layer without having to understand all the details. They also raise a question of who makes what decision in a network. And we often think of that as, what layer makes what decision, or what layer is responsible for a particular type of functionality. But remember, humans make decisions about that functionality, right? For instance, if we decide that we're going to allow for this style of in-network resource management, say we're going to do priority queuing, someone has to make a decision about what traffic gets priority and has to think about what are the consequences for the non-prioritized traffic, right? And even back in the very early days, the early days of computing, but also the early days of this class, when we were thinking about Unix, Unix was designed for programmers by programmers, right? We still use it today. Who was a programmer when it was designed, right? How does that affect the way we use computers today, right? So what are you supposed to do with all of this, right? I've now called out sort of all of these questions, and there were a bunch of other ones that you've seen in recitation and in lecture. This is not the day where I'm going to tell you, here's the answer to how the root zone should be run, right? Here's the answer to how to prioritize traffic, right? But if you are going to go out into the world and design systems, every decision that you make has an impact, right? It's not just an impact on you or on your company or even just on your users, but on the outside world as well. And you can enable people to do really amazing things with these systems. You can also disenfranchise entire communities, right? You can ruin the environment. If you're not going to go out into the world and design systems, if you are like, I am so sick of this class, I don't want to see a computer system ever again. If no one says DNS to me for the rest of my life, I'll be so happy. You can still look for their impact everywhere. You can understand the power that they hold in the world, right? And whatever field you do go into, you can look at how your design decisions affect people and communities around you, right? So if I could kind of leave you with like one thing to remember this class by, it would be what I think was my favorite in the new segment, which is when we were talking about queuing and we talked about Sally Floyd, right? So Sally Floyd worked on some of the absolutely most detailed networking stuff that there is. I think that Sam and Karen will agree with me. Her work was so low level. It dealt with individual packets and the decisions that a switch makes about this specific packet. And yet the overriding theme of her work was to think about how to make the internet work for everyone, no matter what style of connection they had, no matter how much money they could pay to get faster internet, right? There is no detail in these systems so small that it doesn't impact people. So where can you go from here, right? Where can you go next? I am gonna use the power as I have as a person giving this lecture to talk about a specific class first. If you liked what I was talking about just now, and really what we've been talking about the whole time, you take this class in the fall. So it's a special topics class that I am teaching in the fall. We are going to explore how technical decisions in computer systems impact human society, the environment. We are also going to work on developing a framework for thinking about these decisions so that we can bring that framework back into O33, hopefully next year or the year after, so that thinking about how the decisions we make affect everyone is a more consistent part of the design process. This class is going to be fewer than 400 students, so I am pretty jazzed about that. But that is not the only class that you can take if you enjoyed O33. So I know that a lot of students come out of O33 and say like, well, you know, I like parts of it, but not other parts, which is fine. You know, if you like the operating systems part, you can take operating systems. This class is taught by people who have taught O33 in the past, so we're all coming from the same place. If you like networking, you can take computer networks. I believe that Hari is teaching this in the fall along with Manya. If you like some of the transactions, fault tolerance kind of stuff, the database class, that is pretty cool. Also A24 and A26, A24 is distributed systems. It is a very natural follow-on to O33 if you sort of like the design style thinking of O33, A24 is a great class. If you like security, there's a bunch of stuff to do. I'm gonna let Henry take over for a second and tell us about this first one. Henry, I hope I got the number and the title correct.
Yes, you did. Yes, you
awesome. Did. Tell us about this class.
Can I actually share screen for 1 minute?
Oh my gosh. Oh my gosh. Yes.
I'm so ready. Let me see if I can do this. Host disabled participant screen sharing. Security.
You're muted, Katrina. Okay, you should be good, Henry. You should be good.
All right. Cool. I'll be fast, but can you see this? Awesome. All right, so I'm super excited to tell you about this class. It's a new undergrad class called SIG Security, also known as SIG S060. So the idea of this class is to give you kind of 50% system security and 50% crypto, so that you can like learn how to define and reason very precisely about the security and privacy guarantees that a computer system can give you. And then the other part of the class is how do you actually construct and use the most important tools in secure systems design and cryptographic systems design. It's like build systems that do interesting things. So there's going to be some like pen and paper problem sets, but actually the overriding kind of chunk of the work in the course is going to be building up over a series of labs your own encrypted messaging app. So I'm like, I think this will be really, really fun. I'll be, can I get one more minute, Katrina? I'll be fast.
Henry, you can have all of the minutes.
I can have, I can have the rest of the week. I guess this is the last lecture. So I guess just to give you a flavor of like the kind of things we're going to talk about. So in 033, we talked about process isolation. It's like a really important principle. And this is super useful, super cool. I think of it as like kind of bicycle level coolness. In 6 security, we're going to talk about like really powerful tools, like non-interference is a way to reason about isolation in computer systems and hardware enclaves and program verification. On the crypto side, we talked about digital signatures. Again, like beautiful, beautiful, simple idea that's like used all over the place in computer systems. And in 6 security, we're going to kind of like take this to the max. We're going to talk about post-quantum signatures, encryption schemes, differential privacy, how these all fit together. And I think what's unique about this class, and is the first time it's happened at MIT, is we have a mix of like theoretical crypto faculty members and system security faculty members teaching it. So Yael Kalai is a theoretical cryptographer. Srini Devadas has done hardware security stuff. Nikolai Zeldovich is like our system security expert. And then we have 2 fantastic TAs. So I guess I want you to think about, if you're thinking about what to do next, 6033 is a prereq for 6 security, but this is kind of potentially the gateway into all these other advanced grad level topics at MIT. So if you want to take applied crypto or grad security or theory of crypto, 6 security will like prepare you for this. And then you can go on to do like amazing things in the world afterwards. But if you're not interested in grad level security and crypto, I think this is also the right class for you to take. So you take 6 security, and then you can take like, climate change classes or neuroscience or ancient philosophy, and you'll have a much better understanding of how computer security and crypto kind of relate to everything that you see in the world. And you can also, all of your dreams will come true after that. So I think whatever you're planning to do, I hope that in the fall as you're picking classes, you'll think about security and crypto as like a good next step. That's it.
Amazing. Henry, I haven't scheduled my class yet. I'll make sure they don't overlap so that students just take those 2 classes next semester.
Absolutely.
I mean, dreams coming true all over the place. I am also, Henry, really delighted by the way that you listed the grad security classes, which could be cool after you take Henry's class, because I also had them listed and sort of set up in a similar way, from more systems to more math. So there are a lot of really interesting security classes. I know that is typically a popular area of 033. I think Henry's class is going to be like a great introduction to some of these other things. And then one other class I want to bring up, which I think Avi will tell us a little bit about, is 6805, which is Foundations of Information Policy. Avi, am I correct that you are TAing for this class in the spring?
In the fall.
In the fall, which, yes, it is the spring right now. So in the fall.
Yeah, so 6805 is a class about the intersection of law and public policy and technology, and how we think about, like modern controversies around policy in the internet. And we talk about things like privacy and cybersecurity and freedom of expression, intellectual property, patents, surveillance, like trade, like sort of nation states, international affairs. It's really cool, and it's taught by some really awesome people who have done, who have like worked in government, but not only have worked in government, but part of it is have worked in government. So I think it's a really awesome class to take if you've been interested in sort of the stuff that Katrina mentioned about computer systems and society, and in particular sort of the legal system, and also like activism and things like that. So I think it's a really cool way to see things we've talked about in 033 being applied to different contexts.
Yeah, I think one student at after one of the lectures in security was asking a really good question about sort of, why isn't there more policy around these things? And what are sort of the sticking points of getting such policy through? And Sam and I were both talking that, one of the issues that is out there is that there is sort of a lack of people with expertise on both sides. So expertise both in law and policy and on the technical side of things. So 805 is a really great class. If you feel like that's a direction that you're interested in, I think it's super cool. Avi will be there in the fall. So like you could have Henry's class and you could take 805, you could take my class. And like, if you thought that one instance of all of us was fun, just imagine 3. So this is where I'm gonna leave you with for the lecture today. You have an exam coming up, but this is the last time I'm probably gonna see most of you. Thank you for sticking with us through this absolutely wild semester. I hope that this is the last lecture I ever give on Zoom. That would be amazing for me. I hope that we will get to teach some of you in the fall, and I hope that we will be in the same room together. So I will stop the share. I will stop recording.